Arnab Hajra, Associate Professor, BITS Pilani, renowned for nano gas vapor sensors and photodetectors. Now, I would like to request FDP Coordinator Mr. Rajesh Singh Shekhawat to welcome our distinguished speaker with the bouquet. Dr. Arnab received his BTech degree in Electronics and Communication Engineering from West Bengal University and Technology, Kolkata, India in 2009. He received his master degree in VLSI design and PhD degree on nanomaterial based chemical sensor devices from Indian Institute of Engineering Science and Technology, SIPPUR, in 2011 and 2015 respectively. Presently, he is working as associate professor in the Department of Electrical and Electronics Engineering, BITS Pilani. He visited Tel Aviv University, Israel in December 2018 and Sensor Laboratory University of Brescia, Italy in May to June 2018 as a visiting scientist. He also worked as visiting faculty at IC Design and Fabrication Center, Department of Electronics and Telecommunication Engineering, Jadavpur University. He has published about 93 research articles in the journals and conference in international repute with a citation of 1549. His present research interest includes metal oxide, gas and vapor sensors and other semiconductor devices like resistive random access memory. He received Best PhD Thesis Award by Indian National Academy of Engineering. Without further delay, let us warmly welcome to the stage Dr. Arnab Hajra, who will be sharing his expertise. Please, sir.
Good morning, everybody. Myself, Arnab Hajra. So thanks for the nice introduction. Also, thanks to the organizing committee for inviting me to present here. So this is my first time visit in BKBIT, so I'm excited because after joining here in BITS, I've seen that we have one neighbor institute, but I have not visited any time. So this is the first my opportunity to visit here, so I'm very much happy here. So here, when I have seen this topic of this FDP's semiconductor excellence, so I was delighted that because I'm working in that same area. So I decided to talk on this topic, which is written here, that journey towards advanced field effect devices. This particular topic, it's a very general topic. It shows some evolution of field effect device, how that evolution was happened, starting from the invention of field effect device like MOSFETs and how we are moving towards at which direction in the present day. The whole thing will be discussed within this topic. Actually, I get motivations to discuss on this topic when I have joined in BITS. One subject was given to me to teach, that is called the Advanced VLSI Devices. It was a very new course and I configured it. So the course structure is very similar like this talk, and it was my first motivation to think on that way. Okay, not only the devices which is available on books, no, not that. So just collect the materials from different sources and try to think that exactly at which directions we are moving. And now in recent days, when I think about my research, so I'm working on that area because some advanced materials based field effect transistors we are also fabricating in our lab. I will show you some ideas on that at the end of this presentation. So now, here, this is the outline of this talk. So outline I have prepared in that way. So first is the brief history or brief historical perspective of the evolution of field effect device, exactly where we are, we will discuss first. And then I will discuss the basic things, that is a simple MOS system or metal oxide silicon system, because I think you have enough idea about that, but to continue the whole thing, few selective portion should be important to discuss at the beginning. So metal oxide system, silicon system, MOS system we will discuss, and in continuations very briefly only the important portions of the MOSFET we will discuss here. Then we will move to our most important portion, that is the MOSFET scaling and short channel effects. We will try to see exactly what are the problems we are facing due to the miniaturizations of the device. Specifically, that is called the short channel effects. We will discuss on that because that is the motivation to the researcher to choose some new materials, new devices. Okay, so from here, the turning towards the new devices are basically the multi-gate MOSFETs, and one of the ultimate solution is the FinFET. Okay, but before going to that, we will discuss one very important topic that is called the SOI MOSFET, silicon on insulator. That is kind of a linkage between these conventional MOSFETs and the multi-gate device. This device is not commercially famous because, okay, SOI based devices are chips are available, but this is not get the enough success in commercial point of view, but this is showing a better linkage between this conventional device and the advanced devices. We will discuss that SOI MOSFETs briefly. Then we will see that now the recent trends of research on these field effect devices. If you see, then in the recent time, we are moving towards different advanced materials. We are exploring different materials. You know that terms of CNT, carbon nanotubes. We know that graphene. These are the popular advanced materials. People are trying to develop devices by using these channel materials like CNT, graphene. Not only that, they are working with different advanced materials like chalcogenides, 2D materials, basically chalcogenides. They are working with mexins. They are working with black phosphorus, hexagonal boron nitride, so many new materials they are using as a channel material to develop new field effect devices. But not necessarily all those devices are comparable to this conventional silicon technology. But these are the advanced research. Exactly in that domain we are working. So I will give you some idea on that exactly what we are doing and how we are trying to move towards the some new kind of field effect device. Not necessarily it will be only used on the mainstream electronics, it can be used for any other applications also. So in that way, we will move. So this is our full outline and the flow of talk. In that way, we will proceed. Okay? So we can start discussion on historical perspective. So if we see that 1947 is an important time because BJT was invented at that time. BJT is the bipolar junction transistor, and after the invention of bipolar junction transistor, there was an unprecedented growth of semiconductor industry. And this invention creates enough impact on the way people work and their life. Then the device dimension was miniaturized continuously, and slowly we moved towards the VLSI technology, very large scale integration technology. So what was the benefits of this miniaturization of the device and moving towards the VLSI? The device, we obtained the higher packaging density, higher circuit speeds, lower power dissipations. All these are very important points from the integrated circuit points of view. Other than this, we have the superior performance, dramatically reduced cost per functions, and much reduced physical size. If we can discuss all these things in detail, you will see that what is the huge change happened in electronic industries. If we can think about the economic side, integrated circuits business has grown worldwide in sales from $1 billion in 1970 to $20 billion in 1984 and has reached around $250 billion in 2007. So that is a huge economic growth in the integrated circuit market. The electronics industry is now among the largest industries in terms of output as well as employment in many nations. Now we can see the historical perspective, a chronological representations that what are the major milestones we have received till date. If we can see, as already I have mentioned, 1947 is the time when the first bipolar junction transistor was invented. Then the BJT was implemented to construct integrated circuits, and first integrated circuit in 1958. Of course, that is based on bipolar junction transistor. In 1960, that is the most important invention, that is MOSFET or field effect transistors. After the invention of MOSFET, immediately within 3 years, that great invention that is called the complementary MOS structure in 1963. And then we can see within 1970, we have the one transistor DRAM cell in 1968, and 1971, we have the first microprocessor. And then immediately the VLSI era was started. Until date, we are moving in that area, and of course, we are moving towards ultra large scale integrations, ULSI technology also. So this is the historical perspective and exactly at which year the devices were invented. Now, we can see that brief history of this field effect device or MOSFETs. If we can see that exactly the phenomena of field effect, that means we will apply one voltage externally and will control the conduction of the surface of a semiconductor. That particular phenomena was first proposed in 1930 around. That is clearly before the BJT invention. Okay, that is around 1930. But at that time, this phenomena was not clearly observed because the problem of fabrication, because that silicon dioxide interface, there was a lot of different charges. We know that is 4 different types of charges that exist on the surface. That was huge in number, and the effect of field was not clearly visible at that time. And that is a mistake, and that's why almost 30 years we took to get the particular MOSFET device, and when it was conceptualized in 1930 but invented finally in 1960. What happened within these 30 years? In these 30 years, BJT was invented. In the meantime, what happened that fabrication process was improved. Only that silicon dioxide system was improved quite. That's why that interface charges, which was created problems at that time, was removed. And then in 1960, first time that field effect was clearly observed, and then immediately it was implemented for fabricating the MOSFET device. Then if we see from 1960 to 1970, N-channel MOSFETs, P-channel MOSFETs were simultaneously used with bipolar junction transistors. Equally, they were important, but they have their individual advantages. Bipolar junction transistors are very much faster device, okay, but MOSFETs are quite good for the integrations point of view. Okay, so both have their individual advantages, but the biggest achievement was at that time when the CMOS was invented, because if we see that single polarity MOSFET circuits suffered from large standby power dissipations, and hence were limited in level of integrations on a chip. When the CMOS was invented, there was no limitation to choose any such kind of device for using VLSI technology. So this is the history and background we can say for behind this field effect device. So when I say that field effect device, it is quite a general term. It can be considered as junction field effect transistors. It can be considered as our MOSFETs. So there is lots of situations, but I can only mention this field effect device term so that we can choose any device other than MOSFETs. Okay, just to keep that options open when we will think the advanced devices, we will see there is a options open. This is not the MOSFET, only the field effect device. Okay, so in that way, we will move to our next topic, that is the MOS system. Very briefly, I will discuss it. because it will help us to realize the next portion. So, if we can see the metal oxide silicon system, that is an important invention, that is growth of silicon dioxide on the silicon substrate. That invention is actually the main reason for this great success of this MOSFET and field effect device. That easy growth of silicon dioxide layer over the silicon substrate by the thermal oxidation is the actual point. And this quality of this oxide is very, very good, and the thickness was very much controlled. Okay, and if we can see that property of the silicon dioxide, it is a quite an ideal insulator, shows that band gap around 8 electron volt. So all these ideal properties are easily available with silicon dioxide, and which can be created by 1 or 2 step thermal oxidations on the silicon substrate. That is the great importance. Then if we can choose any metals over this silicon dioxide substrate, we can construct a metal oxide semiconductor system. That is the most important part of the field effect device, and simply we can say this is the MOS system, MOS junction, MOS capacitor. Any way we can represent it. This is the third important junction for the electron device area. What are the other two junctions? We know that metal semiconductor junction is one of the important junctions, that may be ohmic type, that may be Schottky type. Another junction is the PN junctions. PN junctions can be homo junctions, can be hetero junctions, okay? That may be PP junctions, NN junctions, that means any junctions between two semiconductors. Any junctions between metal and semiconductors. These are the two types of junctions, and this is the third type of junctions where metal, insulator and semiconductors, three types of materials are simultaneously used. Okay? Now, the metal semiconductor junction and PN junctions, they are characterized with IV characteristics, current voltage characteristics, because if we apply one voltage, current will start to flow through the junctions either in forward bias or in reverse bias. But this MOS junction, this is not like similar junction, because if we can apply some voltage between this metal and this semiconductor contact, no current will flow, because they are separated by this insulator. So simple IV characteristics is not sufficient to characterize this junction. Earlier two junctions we can characterize with IV characteristics. In any interview we ask, okay, draw one IV characteristics of PN junction, draw one IV characteristics of MS junction. But we can say IV characteristics of MOS junction. But how we can characterize it? We have to measure the capacitance voltage measurement, CV plot. Then only we can characterize this junction. So here I have shown one CV characteristics here to characterize this, because this structure is just a capacitive structure. You can assume this, this is the metal part, and this is the silicon substrate is also doped. So these are the two parallel plate, and silicon dioxide is the insulating part inside there. So it's ultimately a capacitive structure, and to characterize it, we have to follow the CV characteristics. Okay, this is the typical CV characteristics. I am not going to discuss on that. We can just think, when we will discuss the operation of this MOS capacitor or MOS junction with under different voltages, because that will be considered as the field effect. So we will consider this MOS junction as the ideal junction. What is the difference between ideal and non-ideal junction? When we will consider this MOS junctions or MOS capacitor is ideal, we will consider the contact potential. That means the work function difference between this metal and this semiconductor will be 0. There is no contact potential, that means no work function difference. That is the ideal situation. We will just assume it, and later we will just ignore it. And the second assumption is the interface charges. Interface means silicon dioxide interface. That particular interface is have no interface charges. Really, we know there is 4 different types of charges: interface trap charges, oxide trap charges, fixed oxide charges, mobile charges, but we'll consider they are 0 initially. And with these two assumptions, we have the ideal MOS capacitor. Now we'll try to understand its operation. So here is the typical energy band diagram of this MOS system. We have the metal here, and here is the silicon dioxide, our insulator, and this is the semiconductor. Now, if we can consider the ideal situation, so you can see this, it's not continuously showing, okay. I can show it here directly, no problem. Okay, so if we can see that structure that our ideal situations is showing or not. So this is the Fermi level of metal and this is the Fermi level for the semiconductor. They are exactly at the same line. So the work function which we will measure from this vacuum level have exactly same distance. So work function is exactly equal. So work function difference is 0. Okay, so this is the ideal structure. Now, under these situations, what you can see, this semiconductor side, conduction band, valence band, they are flat. So, we can say these are the flat band conditions, and under these situations, if we try to see the electron and hole concentrations of the semiconductor side, there can be represented with this straight line. So, suppose this is our, okay, sorry. Yeah, that's fine. So now, this is the typical energy band diagram. So now here I'm just trying to show when the voltage is 0, that means the voltage between metal and semiconductor is exactly equal to 0. At that condition, if the MOS junction is ideal, the hole and electron concentration, they are constant for this interface towards the bulk region. Okay, that simple thing we have considered. Why we have considered the hole as the top? Because this is the p-type substrate and Fermi level is close to the valence band. So this is the hole is the majority carriers and electrons are the minority carriers. Well, now we are applying the voltage between these two terminals. So V equal to 0 should not be applied here. So V less than 0, V greater than 0, V much greater than 0. These three conditions we will see. Here is the typical energy band diagram and here is the electron and hole concentrations and their variations is simultaneously showing. So here this is the accumulation conditions. What is the accumulations? If we can apply a voltage which is less than 0, that means a negative voltage. Negative voltage we are applying at metal side with respect to this semiconductor. So application of this negative voltage to the metal, what you can see that hole concentrations near this interface will increase. At the same time, the electron concentration will decrease in the same order. That is happened due to the polarity of the charges, because we are applying the negative charges, so negative charges will be here. To compensate that negative charges, some positive charge will appear at this interface side. That's why this situation is happening. But the most important thing is that when we are applying this voltage, no current is actually flowing, because no carrier is flowing, because this portion is an insulator and through insulator no carrier can flow. What happened? Only the interface region, hole concentration is increased, at the same time the electron concentration is decreased. So that situation says that Np equal to Ni square, that is the mass action law, is still valid after application of the voltage. So the equilibrium condition is maintained here after application of voltage, that clearly observed here. And here the situation we can see that hole concentration is increased, so at the interface region, so that is called the accumulations of the majority carriers, or this is the accumulations of holes, we can say. Now if we can apply the opposite polarity, that means positive voltage at the metal with respect to the semiconductor, so the hole concentration will show the opposite situation, that means it will try to decrease, and simultaneously the electron concentration will try to increase. Again, the Np equal to Ni square, that mass action law will be maintained, because equilibrium is still maintained after application of some external voltage. That is a very interesting thing for this MOS junction. Now it completely depends on the amplitude of this potential. If the potential is increased further, we can increase this potential, then the hole concentration can reach exactly at the intrinsic level. Electron concentration simultaneously will reach at the intrinsic level, because Np equal to Ni square always be maintained. That situations may arise. And if we can increase this voltage further, then it can cross them. And if the voltage is sufficiently high, you can see the situation, the electron concentration, which is minority carriers, is exactly equal with the hole concentration, which is obtained from the doping. And this whole concentration is exactly decreased, and the Np equal to Ni square is still maintained here. This is the situation is called inversion, and earlier AD situation will be considered as the depletion. So inversion, we can say this particular condition when the hole concentrations is equal with electron concentrations. We will not say the whole concentration, we will say the electron concentration at the surface will exactly equal with the doping level of this semiconductor. Then we can say the strong inversion is started. Before that, we have the weak inversion, and earlier we can say these are the depletion. So in that way, we can discuss these operations, but I think you know these things, so no much detailed discussions will not be required because our objective is slightly different, so I'm skipping this. So here is the brief on this MOS junction with their charge distribution, field distribution, and the potential distribution. Quickly we can discuss it. Suppose we are at the edge of strong inversion, that is threshold voltage point. At that point, what we know that positive voltage we have applied, that's why positive charges we are showing, and at the interface side we have the negative charges. What are the negative charges? We have the QD is the depletion charge, and Qn or Qy are the inversion charges. So these are the two types of negative charges. Actually they are balancing positive charge which we are getting at the metal side due to the applied positive voltage. If we can see the field distribution will be looking like this, because the voltage that we are applying to this MOS junction will be distributed among this insulator and the depletion region of this P-type silicon. So the potential which is considered across this oxide is responsible to show some electric field. That is, the electric field in the oxide side is represented with EOX, and this is the electric field in the semiconductor side, which is maximum exactly at the interface and gradually decrease and become zero at the edge of depletion region. Because at the depletion region edge, the neutral region will start, so there must not be any electric field exist. So this is the situation, but one interesting thing, if we can see that ES and EOX, there is 3 times difference, and that is due to the dielectric constant difference of silicon dioxide and the silicon. In silicon, the dielectric constant is 11.9, and in the silicon dioxide, that is 3.9 only. So there is a 3 times difference. That's why the electric field is showing here 3 times. Okay, so here this is 1, 2, 3. Okay, in that way, the electric field difference we can see. These are potential distributions, can clearly be represented with solving the Poisson equations, but here you can see that potential, that is the drop across the oxide, and this is the drop across the semiconductor. So the voltage what we are applying is basically separated and separately draw across the insulator as well as in the semiconductor. So this is the field distributions of the field effect device. This is the simple concept, and this concept always be valid for any field effect device. Okay, that same accumulations, depletion and inversions, and these threshold voltage conditions and the field distributions, charge distributions, and further the potential distribution, this configuration will never be changed. Okay. Now this is the few expressions of threshold voltage, surface potentials, maximum electric field, depletion rate, depletion charges. You know all those things. Here I am just keeping all those things just for your reference. If required, sometime we can take this reference for explaining the next portion. Now we can take the real MOS junction or non-ideal MOS junctions. You may remember at the initially I have mentioned that ideal MOS junction, but here this is the real MOS junction or non-ideal MOS junction. So what we have to introduce? We have to introduce the concept of flat band voltage. That is two things. First thing, we will consider the effect of these interface charges. We will consider only the effect of fixed oxide charges. This fixed oxide charge is basically exists near the silicon dioxide portion from the interface within 4-5 nanometer range. This fixed oxide are exist. These are due to the unsatisfied bonds. Basically, when the oxidation performed, that silicon is not completely oxidized sometime and few bonds are exist unsatisfied form. So SiO2 minus X in that form we can consider, and these are the source of these fixed oxide charges. These are the fixed, that's why they are represented under the box, and the voltage we need to apply externally to neutralize this effect. If there is some positive charge, there must be some negative charge will exist. They will create here some negative charge, and if we can apply the positive voltage here, so that will create some positive charges, the negative voltage to the metal with respect to semiconductor, so that will create some positive charge which will neutralize this negative charge in the semiconductors. So that is considered as the one part of the flat band voltage is represented with minus QF by COX. Similarly, we can introduce the contact potential, that is the metal and semiconductor work function difference. So because ideal situation never be maintained for any practical situation, so this metal and semiconductor work function difference we have to consider here. So their combination is represent the flat band voltage. In that way, we can finally represent the threshold voltage expression for N channel device and threshold voltage expression for the P channel device. N channel device when the P type substrate, P channel device when the N type substrate. Okay, so these are again the basic concept what we have used here. Now we will move to our next topic, that is brief discussion on MOSFET. If we can see the background history of MOSFETs, so first, as I have mentioned, it was invented in 1960 and it was matured around 1970. Then it was started to use in integrated circuit. So if we can see that history from 1970 to 2020, there is a gradual miniaturization of the gate length or channel length. Gate length, you know, that is the effective distance from source and drain. So gate length is the feature size of the MOSFETs that is gradually decreasing when the year is increasing from 1970 to 2020. You know the Moore's law. So depending on the Moore's law, it has been it followed completely, and around 2000 you can see the gate length is around 100 nanometer, and when the gate length is reduced than 100 nanometer, the problem comes. Problem comes means we are not able to miniaturize the device in the same flow or same linear fashion. Why this problem comes? Because the short channel effects become prominent. So when the device dimensions or gate length is below 100 nanometer, we can say the problems start to show. What are the problems? That is one of our major objectives to discuss. So we will see that what are the short channel effects. But before that, quickly we will see the brief operations of MOSFETs. So here these are the classifications of MOSFETs, can be considered as N-channel enhancement type, N-channel depletion type, P-channel enhancement and P-channel depletion mode device. Enhancement, you know, that is normally off device. Depletion is called the normally on device. This concept is important because in advanced devices, sometimes we can see the field effect device is normally on. That means no voltage is applied, device is on. You are applying certain voltage, so that is called the threshold voltage when the device is off. That is one condition. Sometimes we can see the device is normally off, but you are applying some voltage and then the device become on. That is normally we know for the MOSFET case, so that is called the enhancement type. So we'll discuss the enhancement MOSFET here. We can also discuss the surface channel device and the buried channel device. I will not extend this discussion here. So I can come to the basic characteristics of MOSFETs. You know, this is the typical structure. I will just show you that all the three types of junctions exist within this MOSFET. First, the MOS junction, what we have discussed, that is the heart of this device, metal oxide semiconductor. So this is the MOS junction, heart of this device. We have the source and drain. They are the highly doped region, and this is the N plus source, this is the N plus drain. They are creating some PN junction. So this N plus source with P type substrate, there is a PN junction, and here this N plus drain and this P type substrate is a PN junction. So we have the MOS junction, we have the PN junction. Other than we have the metal semiconductor junction also. If we can consider this metal portion is creating a junction with this source, so this is the MOS junction. MS junction, this is another MS junction, but for this operation perspective, we need this MS junction as a ohmic type in nature. They should not be significant here. If we can see the device structure, they are identical in two sides. So now here we can see the current voltage behavior. Current voltage behavior is looking like the typical MOSFET characteristics can be divided in 2 or 3 regions. Here you can see we have divided it as linear region, nonlinear region, and saturation region. But for the mathematical representations or modeling point of view, we consider up to this portion as the linear region, and from here to rest of the portion is considered as the saturation region. Yeah. Yes, of course. Yeah.
So sir, I have a question. It is like there is a structure side. There is an oxide layer is there at both the ends.
Oxide layer, yeah. This portion.
So why it is so?
Their isolation.
Okay, for the
Because this is the only single device. Okay. Because immediately after that there will be another device. So you are using a common substrate. Okay, sometime. So you are fabricating one device. This is not the only one device. There will be a million of devices. Okay, but they have been separated by some separations. Is another oxide layer will be required to separate it from another device. Okay, where is the separation required? Always the oxide is used. Okay, different oxide, but these are not the growth oxide. They are the epitaxial growth. That means this oxide is created by the thermal oxidations, but this oxide is a epitaxial growth. That is another method. MOCVD method is used. Okay, so these are for the separations. So now this is our typical characteristics. So now if we can see the operations, I will not discuss much because again these are the common thing you know. So these are the linear operations and non-linear operations and the saturation operations. We can see the channel conditions where the channel is almost continuous because the condition that VGS minus VT is much greater than the VDS. So that condition is maintained. So this is falling in the deep triad region or the linear region. We have the continuous field and continuous channel we have. So we must see that our channel is behaving like a constant resistance. So it's a linear resistance almost, and we are getting the linear behavior. If we can consider the linear and non-linear combinations, so we can see that due to the significantly high VDS voltage, we have the channel is reduced near the drain end, but that particular conditions what is showing here is called the pinch-off conditions. That channel is exactly zero at the drain end, and at that particular point our saturation will start. So that is called the pinch-off conditions, and this is the conditions where the channel is significantly reduced. Okay, and the effective channel length is now modulated here. That is called the saturation conditions. Sometimes confusion comes that why we are increasing the VDS voltage further, but channel is reduced, but we are getting the constant current. So sometimes this type of situation comes. But I will not discuss this whole thing. I think that you know these operations. So we can move to the next important thing. So here I will not discuss it much. So these are the MOSFET equations I have summarized here. I am not want to discuss this. I just want to say two important things here. These are the popular MOSFET equations, because if you look at equation number 1, equation number 2, these are the linear and saturation region equations. So everybody know this. So all these equations what we are using here, they are based on the one approximation is called the gradual channel approximations. Okay, this gradual channel approximation is important because this is practical for any long channel device. But if we can consider the same approximation for the short channel device, the device gate length is very small, then this approximation will not be valid. There will be lots of error comes. So the equations what we normally use as the MOSFET equations, that based on one significant approximation is called the gradual channel approximations, and the equations that we are getting here is called the square law equations. But these equations are well popular, and for any circuit implementations, these equations are used. But here, from the device point of view, we can write more accurate expressions where the gradual channel approximation is not considered, and these equations are called power law equations. Again, these equations are exactly representing the same MOSFET, but this is quite a lengthy but very difficult to use for the circuit analysis thing. So that's why these power law equations are not accepted for circuit simulations, but still from the device perspective they are much accurately model the behavior of the MOSFET device. So these equations can be applicable when we will move towards the short channel device. Otherwise, if we can try to use these equations with gradual channel approximations for the short channel device, there will be huge error. Okay, that's why I'm showing these equations here. Yeah. Yeah.
You have shown these equations, and I want to know, like you have said, these equations are for short channel. So, what is the basic length of the channel at which these equations will start to be followed?
There is no such hard boundary.
Yeah.
Okay, there is no such hard boundary. So it's not that after reaching 100 nanometer or 150 nanometer of gate length, this equation will start be valid, this will be invalid. Okay, this is not like that. It's a soft boundary. If you have, suppose a device gate length of 1 micron, safely you can use these equations. Okay,
Like,
it will be gradual channel approximations will be valid.
Like suppose I'm working on 65 nanometer or 90 nanometer. So usually what I have seen is people like they are using these equations like square law equations in their work, and they are not moving on to these power law equations. So right now, because we are moving up to the 3 nanometer, so is there anything like although you are saying that it is a soft boundary, but at least there should be a particular length after which we cannot use those above equations. Is it like that or not?
How much error you will be ready to accept? It depends on that. If you plot the IV characteristics, current voltage characteristics with these two equations, it's audible. Okay, so if with the same, with both equations, you will see the deviation. If you keep that constant mobility model, okay. So, how much error you are ready to accept? That depends. Okay, you think, okay, my intention or target is not that current representation. My target is something different. Follow this one. You try to simulate million of transistors at a time. You will say, no problem, I can manage with that error. Okay, but I will follow only these simple equations, not this equation. So it's completely up to you. There is another options to modify it. Suppose these equations you want to use, but you know this is the more accurate. So what one people can do? People can change this mobility value slightly increased. Okay, so increase or decrease, they can change it. So try to make it match this current level with same level of this, but never be appropriate match, because these are the different functions, this is the different functions, but the level of current will be closer. In a different way, these are the modeling part actually. How we will see, it depends. Okay, if the short channel device, you can think better use these equations from the device perspective. Okay, I'll never suggest a circuit persons to choose these equations. Okay, they'll face problem to work with these so lengthy equations. It will take lots of computational time.
Whenever we are using the software part and like ADS or some other software, we have to put the values of these values, which are already given in the data sheet. So based on that, if we are moving on to the theoretical calculations, the technical one, and if we want to match, then I think the first square equations will be more better.
More better, not only the more better, this is the only acceptable thing. Okay, we show this thing for the modeling perspective, because when we will study a device in depth, okay, so we have to know that what approximations we have taken, and we are obtaining these equations with which type of neglecting that which parameters. Okay, but thing is that if you moving towards the advanced devices, you have to face lots of complex modeling. Okay, and this is one of the hints that if the device becomes smaller, so that situations will be complicated. Here still we are using the classical physics only. We have not introduced any quantum mechanical thing. If you think that really you have the 3 nanometer, 5 nanometer thing, your normal concept will not be valid there. You have to use the volume inversions and so many other issues. Okay, so these equations will completely invalid there. If anyone want to use this classical physics based equations, that's a completely wrong. That concept is completely changed there. Okay, we can move to the next. This is the body effect. Why I am saying suddenly body effect? Because sometime we will see in the advanced field effect devices, they are using only back gate. No front gate is there. Okay, that's why this back gate or body effect is important, because if we can consider in our normal faith, we always think that this is the gate terminal, but we can consider this bulk terminal most of the time connected with ground, with source, that is, it's almost an invalid terminal. But if we can apply a voltage between bulk and source, of course, we have to apply the voltage between bulk and source just to keep this N plus P junction as under reverse bias. This N plus P junction must be in reverse bias so that this PN junction will flow a very, very minimum current, but the voltage will be sufficient for creating some additional negative charges here. Negative charge means negative space charge I am indicating. So this additional bulk to source voltage will be sufficient for modulating this threshold voltage. Okay, so the negative depletion charges will increase due to this application of VV less than 0, because we are applying a positive voltage here with respect to this, so it will attract, negative voltage here with respect to this source, so this will attract the mobile holes that will create some negative charges, that is Na minus will be, so that ultimately decrease the inversion charges. We apply more and more gate voltage to create the same channel. That is the concept, and based on that we can see this is the threshold voltage shift, and this situation, this expression popularly we have used for represent the threshold voltage shift due to the application of external bulk to source voltage. Now think the scenario if we have not the top gate. Top gate is not exactly existing, okay, and we are only considering this back gate voltage to create the channel and to play some operations of field effect device. That's why this thing I have discussed, at the end of this discussion when we will consider the 2D based field effect device, we will see all the devices are only back gate device, and that is much easier to fabricate. Okay. Now the one important point, that is subthreshold conduction. Without discussing this subthreshold part, we should not compare this device performance for the short channel devices. So here this is our current voltage behavior, but this current is ID and this voltage is VG voltage. So if we can consider the drain versus VG, so this is almost a linear increment, or further it would show the non-linearity. So this is the situation when we can represent this current versus voltage in a linear scale. When we represent in log scale, we can see below this threshold voltage, here is the threshold voltage, below this threshold voltage here in the linear scale, we are not able to see any current. Okay, but when we will represent it in the log scale, we can see there is a rapid transitions or decrement of current, which was considered here as zero current, but that is not really zero, but it's a finite current, but the value is small. That current is minus 10 to the power minus 6, 10 to the power minus 8, 10 to the power minus 10, that indicate we are in the micron, nano ampere range of current here within this part. So that is called the subthreshold part, below threshold part, where the current is rapidly decreasing. Okay, but this part will be very much important, because when the device will be off, because most of the device during the operations will remain off, and the off conditions below threshold voltage, if the VDD is already connected, so current should be as low as possible for the low power consumptions. Okay, that is the most important thing. So this slope should be as steep as possible. That means when we will be below threshold, immediately this current will be decreased. So that is our subthreshold slope, and this slope we can consider that indicate the change of VG with 1 decade change of IG. Okay, so most of the time we consider this surface potential below this twice psi B, and the psi B is considered as the region to calculate the subthreshold current, and that is called the weak inversion region. Okay, so now Here you can see the different regions. We have the VDS versus VGS representation. We have the region of linear and parabolic. This is the saturation region, and below threshold we have the subthreshold region. We have derived the equations for linear region. We have derived the drain current equations for the saturation region. We can also derive the equations for the subthreshold region. But in the subthreshold region, our simple drift mechanism will not be valid. We have to consider the diffusion mechanism. However, I am not going to that. I am just considering the equations, but this equation 2 is considered as the drain current equations for the subthreshold region, and which is sometimes almost independent of the drain to source voltage. It is only depending on the surface potential. Considering this equation 2 and 3, we can get an interesting representation of subthreshold slope, that is called the subthreshold swing also, is the ln 10 kT by q COX plus CD by COX. So these expressions, I think you are familiar with that. This is called the subthreshold slope, and for different MOSFETs, this equation is used to represent their properties of subthreshold region. So how better the subthreshold behavior is can be represented with these equations. Okay, so now the essential parts we have discussed. Now we'll move to the MOSFET scaling and short channel effects. So MOSFET scaling, I think everybody you know this. I'm not going to discuss in greater detail, only few points. We know there is mainly the popular scaling is the constant field scaling or full scaling. What is the meaning of constant field scaling? We can say that we have the device have the dimensions. Let's say we have the gate length L. We are reducing the gate length by using a single scaling factor. At the same time, we are decreasing the voltage, VDS voltage, with the same scaling factor. So what we will see? We will see the electric field is constant. That's why this is called the constant field scaling. If the electric field is constant, there will be no problem with the device performance. But that is not practical all the time. We can decrease the dimension of device, but we will not able to decrease the dimension of the applied voltage, because the additional peripherals, they have to use with same voltage. So we can change a particular IC, but we can't change the whole scenario, whole circuits. That's why the constant field is not practical all the time, but this is considered as the ideal situation. We can consider the simple scaling of different dimensions. You are familiar with that. We consider any scaling factor. Let's say kappa is the scaling factor, and we can reduce the parameters of L. We can reduce the parameters like oxide thickness, that is represented with D, by using this scaling factor, and we can decrease the junction depth RG with this scaling factor. We can decrease threshold voltage. We can decrease VD. But if we can consider this NA or doping of this substrate, we have to increase the amount by this scaling factor, because ultimately this doping should be increased by the amount of scaling factor, because the depletion depth, that is depending on this doping also, the depletion depth is a dimension. This WD is a dimension. It should be scaled down with scaling factor K. If we have increased this doping, then only the depletion depth will decrease, because we know the depletion depth expressions that doping should be increased, then only the depletion depth will decrease. Okay. So in that way, this is the normal scaling thing that we can follow for reducing the dimensions as well as the voltage. If one can decrease the length with this scaling factor, one can decrease the voltage with the same scaling factor, so they will get the constant field. So field is not scaled down, that is constant for any devices. Okay. At the same time, we can consider these three important parameters. They are the advantage of scaling. Propagation delay. Propagation delay, we can see that scaled down by this scaling factor K. That means your device will be faster. If one can say that what is the advantage of scaling, not only the miniaturization of the device become faster when we scale down it. If we can consider the power consumptions, it is scaled down by the K square, by the scaling factor square. So power consumption wise, the device will be much improved. Okay, so that is another most important advantage of scaling. And finally, the circuit density. Of course, more and more number of transistors can be accommodated on a single IC. Okay, so we can see that K square is multiplying with N by A. N is the number of transistors, A is the unit area. So the circuit density improves, power consumption improves, and the propagation delays. These are the three important points of the scaling. So of course people will choose to scale down the device so that their performance will improve. More and more transistors will be implemented on the same ICs. These are the advantages. But at the same time, lots of disadvantage will appear. We can see here the voltage related issue, or that if we can consider the constant field scaling, that is not maintained ideally for the practical situations. Here I have given one statistics just to explain that how that real scaling rules followed year by year. I have given here the statistics of 4 different years: 1974, 1984, 1994 and 2004. And the technologies are basically 5 micron in 1974, 1 micron in 1984, and 0.35 micron, that is 350 nanometer in 1994, and 90 nanometer in 2004. What is the situation for the VDD? VDD is 10 volt, 5 volt, 3.5 and 1 volt. If one can try to check that constant field scaling is maintained or not, they can check from here. Suppose from this 10 years of gap, what we have, the technology is 5 times decrease, okay? But the voltage is only 2x time, okay? So this is not the constant field scaling. If we can consider this 10 years, 1 micron to 0.35 micron, so one can divide this 1 micron with 0.35 micron, and you can divide 5 volt by 3.5 volt. Again, they are not the constant field scaling. If we can consider 1994 to 2004, 350 nanometer, you can divide with 90 nanometer, you can divide this 3.5 volt by 1 volt, they are close to this constant field scaling. So sometimes when the required, then people can follow this constant field scaling, and sometimes they have adjusted by using their required voltage and the dimensions. So we can say that ultimately the generalized scaling or constant voltage scaling are much popular as compared to the constant field scaling. Okay, so these are the whole thing about the scaling rules. Now we will move to our next topic, that is effect of channel length reductions. What happened if we can reduce the channel length? If we can reduce the channel length, so the most important thing we can say, we will lost our gate control. Okay, you can explain these situations with different perspectives, but ultimately the gate control will be lost when we will consider the high electric field, when we will consider the short channel device. So what is written here, even with the best scaling rule, as the channel length is reduced, departures from long channel behavior are unavoidable. So the long channel behavior, which we can consider as the ideal behavior for MOSFETs, we will depart from that. This departure arises due to the two-dimensional potential distributions or high electric field in the channel region. You can assume transverse electric fields, EX, controlled by the VGS and the VBS, whereas the longitudinal field, UY, is controlled by VDS. Now, the long channel device, when the gradual channel approximation we consider this EX is much greater than EY. Whatever VDS value we have, but the gate control will be intact. That means our transverse electric field is much greater than the longitudinal electric field. But when the gate dimension is decreased, that means your gate length is decreased, that means where source and drain is more close. So the VDS value, even it is small value, but the electric field will be significantly high in the Y direction. That is, longitudinal electric field will be significant, and this condition will not be valid, and EY will be sufficiently high as compared to EX, and we will lost our gate control over the channel. So when we will try to stop the channel, stop the device, it will not be stopped. Due to the VDS voltage, there will be some flow of current. Okay? So this two-dimensional potential results is many forms of undesirable electrical behaviors. What are the undesirable electrical behaviors? I have listed here. These are the most popular undesirable situations, and all together are called short channel effects. First one is the velocity saturations. You will not be able to avoid it. Second one, charge sharing from source and drain and threshold voltage roll-off. Punch through and drain induced barrier lowering, normally we know that is DIBL. Multiplications and oxide reliability are called the hot carrier effects. Parasitic effects of impact ionizations at high field, and finally the oxide breakdown. If you can search, you may think two, three more points you can see, but there somewhere flows. Okay. So ultimately, all these things what we are getting summarized here as a short channel effects, they are due to the electric field EX is not sufficiently high as compared to the EY. That's why we are getting all these situations. So we will discuss these short channel effects very briefly, and then we will see how we can overcome this. I have to know the time. Yeah. Keep it here. Okay. So now the velocity saturation. So velocity saturations, you know this. It's a normal phenomena if we have a semiconductor, piece of semiconductor, and if we can apply some voltage on that, and we can see that electron will start to flow, and it has some velocity. And what is the limit of that velocity? Of course, the thermal velocity is the limit. Okay. Beyond the thermal velocity, if we can apply more and more voltage, that is not possible. So when the voltage will increase, initially, it will show some constant mobility situations, and further when it will be close to the thermal velocity part, so the mobility will not be constant, mobility will try to decrease. That is called the velocity saturation, and that is happened when the electric field is very, very high. Electric field, here it is called the critical electric field. When this situation arises, then the velocity saturation will start. First I can explain this very briefly. We have the carrier velocity as per the y-axis, and as per the x-axis we have the electric field. If the electric field increases, the carrier velocity will increase, and the typical characteristics will be looking like this. So if we can consider this portion we have a almost linear increment of the carrier velocity with increase of the electric field. But when the electric field crossing this critical point, then we can see some saturation nature in the carrier velocity. So that is called the high electric field effect, and if we can measure the mobility within this region, mobility will be decreased because mobility is nothing but the slope, but slope is higher here, but slope is gradually decreased in this region, and here this is almost saturated. Now this situation, why it is arised? Due to the high electric field. High electric field can be arised due to two reasons. If we can apply very, very high voltage, then the electric field will be high. Otherwise, if we can decrease the dimensions, then also electric field will be high. Here in the second case is practical, because our applied voltage, VDS voltage is small, suppose 1 volt you are applying. But your dimensions, channel length, you think that is 100 nanometer. And divide this 1 volt by 100 nanometer, and you can think that how large the electric field is. That is the reason we have the velocity saturation occurs within the channel region. Now the high field or extreme electric field is where maximum, it is maximum at the drain end as compared to the source end. So the velocity saturation or critical electric field will reach first at the drain end, and then it can be considered for the throughout channel. What happened? What is the effect of that? Suppose this is your current voltage behavior for this normal MOSFETs where the velocity saturation is not observed. But if the velocity saturation observed, you are believing that your current will show this type of behavior, but before reaching that actual saturation, your current voltage behavior is showing some another type of saturation. For the same device, only the electric field is much higher in here, and the velocity saturation is applicable. So the all behavior is now suppressed, and you are getting the saturation before this actual saturation. So this saturation is not that saturation which we know about the device performance or MOSFET performance. This saturation is due to the velocity saturation. So whole performance of the device becomes changed due to the velocity saturation effect, and that is happened due to the short gate length or short channel length. That is the first and most important short channel effects we can consider here. This is the expression I have written here to represent the VD sat if we can consider the velocity saturation. Otherwise, what we know, VD sat value, that is VGS minus VT for the normal case. But if we can consider the VD sat with velocity saturation, we can use this function. We can move to the next short channel effect. Charge sharing from source and drain. You just think, this is your MOSFET, it's a short channel device. If you can consider the same structure for a long channel device, then this charge sharing effect will not be significant. What the charge is sharing? But you know, this is the channel region, this is the channel region, and this is the depletion region is created due to the VGS voltage, gate to source voltage, and exactly this interface region we have the 1 or 2 nanometer thin inversion charges. But this portion is actually, we have the depletion charge which is created due to the gate to source voltage. But here we have another depletion region which is created due to this N plus P junction. This is the source end. Here is the N plus P junction at the drain end, but this depletion region is much extended because the VDS voltage is applied and this N plus P junction is under reverse bias. So this depletion region is much wider than this depletion region at the source end. Now, for the long channel device, there is no such problem comes because this portion where this depletion region is overlapped. This overlap portion, we can consider this channel contribution due to the VGS voltage is almost only contribution of the gate to source voltage. But for this short channel device, this charge is not only contribution of gate to source voltage, their contribution of drain to source voltage from this drain junction. Here is some contribution from the source also. This contribution of this charge will not be we can ignore here. If the device is too much long, so this type of overlap we can ignore and we can say that most of the charge which is created in the channel region is only due to the gate to source voltage. That is the charge sharing. Okay? If we can consider this charge sharing effect for this short channel device, we can see this is the deviation in the threshold voltage expressions. So this Vt, del Vt is the deviations due to the threshold voltage expression. You can see the one practical scenario when the threshold voltage, how it is changing with the reduction of the channel length. Here we have started reduction of the channel length from 4 micron, 3 micron, 2 micron, 1 micron, and threshold voltage is constant up to 1.5 micron, but it start to decrease when the channel length is below 1.5 micron. Why it is happening? This is mostly happening due to the charge sharing effect, and these calculations we can do by using this formula. Behind we have lots of calculations, lots of derivations, modeling part, but this type of threshold voltage roll-off or degradation of the threshold voltage we can see in case of charge sharing effect, and this thing will be much prominent if the drain to source voltage is significantly high. Here we have two cases, VD equal to 0.1 volt, VD equal to 3 volt. When the VD equal to 0.1 volt, this threshold voltage roll-off is minimum, but when VD equal to 3 volt, there is a significant threshold voltage roll-off. Why? If you can see this portion, the drain will show more and more charge contribution from this PN junction side. So this degradation will be much significant at higher VDS voltage. We have also the expression of Ys and Yd. You can see this dimension. This portion is Yd and this portion is Ys. Sometime to represent the pinch-off conditions, punch-through condition, we can consider this Ys plus Yd is equal with channel length. That is called the punch-through condition. However, we will come to that in the next slide. So this is the charge sharing effect from the source and drain, and due to that there is a threshold voltage roll-off happen. Okay, that is our second short channel effects. We have the third short channel effect is the drain induced barrier lowering. What do you know that DIBL effect? So what is the barrier? Barrier exists at the source end, which has been lowered by the drain voltage, high VDS voltage. This thing can be easily understood from this energy band diagram of these MOSFETs. Let's say this is the energy band diagram for the long channel MOSFETs. So for the long channel MOSFETs, this is our source side. So N plus region. So conduction band is close to the Fermi level, and this is the valence band, and this is the p-type substrate, and here this is the drain side. What we have applied? We have applied a VDS voltage. Due to the VDS, the shifting of the energy band. So this is the VDS voltage. That's why we have this band bending, which we show here, side to the drain. But if we can see the source end, that is intact because source is connected to ground. So there is the barrier already exists. What is the barrier actually? This is the built-in potential between this N plus and P region. So this is the built-in potential is already intact here. But if you can consider the short channel device when they are very source and drain are very close, and with the application of the same VDS voltage, this band bending is too much significant. You can see at this source end there is a change in the barrier potential, and that's why there is a possibility of leakage of current. So what happens for that? If you are applying your gate voltage below threshold voltage and you are applying a high VDS voltage, your device will start to conduct. That is not expected because you are not applying the VDS voltage above threshold voltage. So you are expecting that device will off, but you have applied some VDS voltage and device start to conduction. Okay, start to conduct. So there is some finite drain current at that point. So that is the drain induced barrier lowering. There is some numerical expressions to represent the DIBL also, and this is the expression to represent the punch through condition. So that is our third short channel effects. Fourth short channel effect is the multiplications and oxide reliability or hot carrier effects. So if we can consider the device operations, suppose this source and drain separation is very small because we have the short channel devices. So electrons are moving from source to drain during the operations. Now in this portion, at the drain end, we know there is the highest electric field we have. Due to this highest electric field, the carriers, they are achieving a high kinetic energy. High kinetic energy, we know that half mv square is the energy. There's a very high value, and in this range, and this kinetic energy is too much high that it can cross the barrier of this semiconductor and the silicon dioxide. The barrier is normally called the offset. This offset is around 3.1 electron volt. That is one of the important advantage of this silicon dioxide system. This offset is too much high. That is the difference of conduction band. Conduction band of silicon, conduction band of silicon dioxide. That offset is around 3.1 electron volt. That is too high. That's why when the electrons are flowing through the surface, they are not easily entered to the oxide because of this 3.1 electron volt offset value. But when these channels are very short, electric field is very much high, and these carriers achieve very much high kinetic energy, very much high half mv square, they can overcome this 3.1 electron volt and reach this oxide part. And when the electrons are entered into this oxide, they are not reversible process. They are not revert back to this channel again. They still stay here. When they stay here, then the oxide quality will be degraded. Oxide will become poor, and this situation, if can maintain continuously, then the oxide performance will be poor, and after some time it will be broken down. So oxide breakdown will be possible. So this energized carrier, due to the high electric field that happened due to the short channel effects, that is due to the they are called the hot carrier effects because they are highly energized carrier. That's why sometimes this is called hot carriers. Okay. So this is one, and this is our fifth short channel effect, that is called the parasitic effect of impact ionizations. You can see these situations, what happened. If the electric field is very much high, that means drain and source are very close, electric field very high, so in this portion where the electric field is maximum near the drain end, impact ionizations can happen. You know the impact ionizations, due to this phenomena, electron hole pairs are generated. If the electron hole pairs are generated, due to the bias, electrons will move here, but the hole, mostly they are moving towards the bulk side. When the holes are moving towards the bulk side, they are synced by this synced by this bulk terminal towards the source. That is the natural process. So now, if this impact ionization is significant, then it can show some parasitic effect. What is the parasitic effect? You can think this MOSFETs with N plus source and drain with P-type substrate can similar like a NPN transistors. But NPN transistors will never be active until or unless this impact ionization related phenomena happen. How this thing will be active? If you can believe there is a bipolar junction transistors or NPN transistors, and here is the impact ionizations happen, and due to these impact ionizations, holes are moving from drain end towards the substrate. So in that direction, holes are moving. Substrate have some resistance. So these holes, they are moving in this direction, and what we know, the current will flow in the same direction of hole flow. Okay? So that current will multiply with this resistance and it will show some drop. If some drop is created here, so this is our emitter terminal and this is our base terminal, so base emitter voltage will be significantly high. What we know, if the base emitter voltage is more than 0.6 or 0.7 volt for the silicon BJT, then this BJT will be active, it will be on. If this is on, so now the current can flow through this bulk also. It's not only depends on this channel region, it can start to flow through this bulk. So that is the parasitic effect and not required actually. It's happened due to this impact ionization and high field situation. That is one short channel effects. Finally, the oxide breakdown. Why that oxide breakdown comes? You just think we are losing our gate control over the channel because of because of the short channel of the device. Small VDS is sufficient to increase the EY electric field. Okay. So what is the way to increase the gate control over it? The normal and easy way, decrease the oxide thickness. If the oxide thickness is decreased, we have the higher capacitance and we have the more and more capacitive coupling. That's why the oxide thickness is decreased from the starting days. Now the oxide thickness is very, very small. But what is the problem? The oxide thickness reduction is not the only way to overcome these short channel effects. If we can decrease this oxide thickness, there will be the possibility of oxide breakdown. Oxide breakdown can happen immediately. Oxide breakdown can take lots of time, and after some time, the oxide breakdown can possible. Immediate breakdown can possible when the electric field will be greater than 6 megavolt per centimeter. That is the almost, you can say, a known value. Otherwise, that silicon dioxide can be broken down at the electric field of 18 megavolt per centimeter. But around 6 megavolt per centimeter, when that much of electric field is created, then we can think that there is some possibility of breakdown of the oxide. So we have to consider the oxide thickness such a way that electric field is below of that. Okay? Otherwise, if you have your electric field is sufficient below of 6 megavolt per centimeter, but problem is the time dependent oxide breakdown. That means the breakdown will be happen, but not in immediately. Not in after 1 year or 2 years. Maybe after 40 years, 50 years. Okay. So after some time it would be damaged. There is some procedure to test that time dependent oxide breakdown or TDDB. So these are the ultimate problem if we can decrease the oxide thickness to overcome from the short channel effects. Okay, so these are the whole thing related to the short channel effects and due to the miniaturizations of the device dimensions. Now we will try to find some alternate solutions and we'll move to some new devices. Okay, so before that, if you have any questions, it will be better to discuss and then we'll move to some next topic. Okay, we can move then. So, what we have discussed till? We have discussed MOS junction, we have discussed MOSFETs, we have discussed limitations of MOSFETs if we are going towards the short channel devices. Now, we are trying to find some alternate solutions. There is lots of alternate solutions to overcome these different situations, but really, if you want to overcome one problem by choosing one solution, it will create another problem. Okay, there is no such ultimate solution. Ultimate solution, change the device. Okay, so here I will discuss silicon insulator SY MOSFET because I believe this device is the linkage between the conventional MOSFETs and the advanced MOSFET. This particular type of MOSFETs never get enough commercial success, but it gives a better idea that how we can move towards the double gate device. Okay, how we can increase one gate, another gate, and then we can increase the gate control over the channel. It gives that idea. That's why I believe this is the link device. When we were in master degree, that time this SY device was so popular and lots of research article was there. We tried to study it, but then slowly that discussions were stopped and people moved towards multi-gate devices. But really, that is a interesting and important concept. That's why we are now moving towards the FinFET today. Okay, so it was developed in early 1980s. The concept was first developed, and this is developed by these scientists. And we have lots of study materials from Professor J.K. Collins. So based on this SY MOSFET, and most of the thing we have adapted from his valuable books and research articles. Now, that first time this SY adoption was taken for high performance computing applications, and it was sometime used in military applications and some power applications. It was invented targeting towards some specific applications, but it became popular. So three major SY wafer companies are now, they are popular, like SY Tech, SHE and Sun Editions. They have the total capacity of 2.5 million wafers per year. Now, what are the advantages of this SY MOSFET? Why people are choosing this device over the MOSFETs? Sometimes due to the low junction capacitance. That's why the overall capacitance become lower and the propagation delay is better. That's why this device is ultimately a faster device than MOSFETs, and body effect is reduced and soft error immunities. These are the few important points. That's why people have chosen this SY MOSFET. But I have added this SY MOSFET here as a linkage between single gate device to the multi-gate device, not for these advantages. So you see the structure here. Structure of this SY MOSFET is very simple. Okay, this is similar like MOSFET. This is our simple MOSFET, conventional MOSFET, source, drain, substrate, gate oxide. But here, the same structure, only we have a buried oxide layer. This oxide is nothing but silicon dioxide, but the thickness of this oxide is much more than this oxide thickness, the top gate oxide thickness. Okay, so this is the only change. You have the silicon substrate, you have the buried oxide layer, that is a thicker oxide layer, and then you have a silicon body. Okay, this is called the silicon body, and the thickness of this silicon body is called the TSI. Okay, and some portion of this silicon body is doped for the source portion and doped for this drain portion, and rest of the portion will be considered as the neutral portion, where the channel will be created due to the gate voltage, VGS voltage. Okay, so this structure can also be implemented over the quartz or glass substrate, replacing this buried oxide layer. Okay, but this is the more popular structure. If we can consider the ultimate steps for this fabrication of this SY device as compared to the bulk silicon MOSFET. Bulk silicon MOSFET, the fabrication starts from bulk silicon wafer. You have only a silicon wafer, you start fabricating from here. But for the SY device, we initially consider a SY wafer. Okay, silicon, BOX layer and SY layer. This is the initial wafer structure. So if you want to purchase SY wafer from market, you can purchase it. SY wafer is available. Okay, thus commercially this wafer is produced, and then simply by removing some additional portions from this top silicon layer, so they are etched out, and then some portions is doped, and then the oxide growth, and then metal depositions. After few fabrication steps, easily this SOI MOSFET can be fabricated. Okay, so what is the difference again? This is a silicon body we have. This silicon body easily converted to source and drain and the neutral portions, and top gate and is created, and this is the buried oxide layer on which the whole device is placed. This is the difference. Now we can see the greater versions of CMOS bulk versus CMOS SOI structure, very similar. This is our popular CMOS bulk, but for CMOS SOI device, everything will be same, only we have the buried oxide layer, and in between we have the silicon substrate. So this is our NMOS, this is our PMOS, they are separated by using the oxide isolations. Okay? Now, what are the advantages? The first and most important advantages is the source and drain capacitance. You can think the junction capacitance are significantly high in the conventional MOSFETs. Junction means, let's say this is your drain N plus region and this is your P substrate. There is a huge junction capacitance due to this N plus P junction. We know that PN junction offers a huge capacitance, voltage dependent capacitance. This is the expression of that capacitance. Okay, the huge junction capacitance we have. But in the SOI device, you can see the drain and source. Immediately after that, we have the buried oxide layer. No junction will be formed, and the junction capacitance will be very, very small. And this capacitance can be represented with this expression. Okay, so that is the most important advantage. That's why the SOI device is much faster than the conventional MOSFET. Now we will see the types of these SOI devices. Mainly, the SOI MOSFETs can be classified in two parts. One is the partially depleted SOI MOSFET, another is called the fully depleted SOI MOSFET. So again, you can see this structure. We have this substrate, buried oxide layer. We have this silicon body. This is the whole silicon body, and this is the N plus region. You can believe this is the drain, this is the source. This is the neutral portions. Now, front gate oxide we have, and what is the situations for partially depleted MOSFET? This is the condition. So this silicon body thickness is TSI. Okay. Now, if this TSI is greater than 2 times of XD max, then this device will be considered as the partially depleted SOI MOSFET. What is the XD max? This is the depletion region width for the MOS junction. I have shown that depletion region thickness for at the age of strong inversion. That is the maximum depletion width. If you can apply more and more gate voltage, so this depletion width will not be increased after reaching the maximum age of strong inversion. So this is the maximum depletion width, and this is the maximum depletion width can be extended from this top gate side, can be extended from the bottom gate side. But this condition says TSI much greater than 2 times of XD max, that says there will be some neutral region which will not be depleted. Okay, that's why this particular device, there will be some neutral region which will never be depleted if we can apply any voltage, any of that gate. So this type of SOI device will be called the partially depleted SOI MOSFET. The operations is very much similar like the MOSFETs. Okay, because of this neutral portion. This is called the neutral body, but there is another significant effect is influence this performance for the floating body effect. But we are mostly interested over this fully depleted SOI MOSFET because this is the way towards the multi-gate device. So this FD-SOI MOSFET is the device which can maintain this condition. TSI or silicon body thickness is less than XD max. That means by applying this front gate voltage, you can deplete this whole silicon body. Okay, so that is the fully depleted SOI device. This particular device have greater significance in operations. They are far different as compared to the conventional MOSFETs. If we can see the energy band diagram, it would be easy to understand. So here we have this MOS structure, normal MOS structure. We have one gate oxide, and this is the band bending because we know the depletion and then inversion happened, that's why this band bending happened, and this is the width of the depletion region, XD max you can believe. Okay, this is the situation when we have this double gate we are getting here. This is the front gate and this is the back gate, or nothing but your buried oxide layer for this SOI device. But this is the partially depleted SOI MOSFET, so the depletion region can be extended from top side, depletion region can be extended from bottom side, but there will be some neutral region where the flat band exists. Okay, but here this is the fully depleted device, so you can think this TSI thickness is much smaller, so these two gates are too closer, so only top gate is enough to deplete the whole situation, whole neutral body. So from the energy band diagram, this device can be easily understood. Okay. Now the operating regions. Now we have two gates. We can consider one is the top gate, another is the bottom gate. So bottom gate, if we can consider as VG2, if we can apply some gate voltage from the bottom side, it can responsible to create some electric field in the neutral region by this bottom gate voltage, and the similar phenomena like accumulation, depletion, inversion can possible by the back gate also. Simultaneously, we know the operations of top gate or front gate VG1. So if we can consider the situations of VG1 and VG2 and try to realize these are the different operating regions. So in the right direction, we can say when the VG1 voltage is increased continuously, so at the negative portions we have the accumulations, and the top directions we have front gate depletion, front gate inversions. If we can go from left to right, our back gate accumulations, back gate depletions, back gate inversions. So we have two gates, individual gates have 3 operating conditions, so of course we have the 9 different operating regions for this device. Okay, so 9 different operating regions, but this shadow portions is actually area of interest. Okay, most of the SOI device, FD-SOI device working within this operating range. Okay, but normally for the calculation of threshold voltage for this fully depleted SOI device, we focus over this region. That means we only consider the top gate VG1 always be in inversion, but the back gate may be in accumulations, back gate may be in depletion, back gate may be in inversion. Within that conditions, we can consider the threshold voltage expression. So we are believing that VG1 is the gate which is responsible for creating the channel, but we don't know the situations for back gate. Back gate may be in any of these 3 operating conditions. Okay, so this is the cases we consider for front channel inverted, back channel accumulated, front channel inverted, back channel depleted, front channel inverted, and back channel inverted. So these are the 3 conditions for calculating the threshold voltage. But I have not shown the threshold voltage calculations because that is really interesting, but that is enough mature. That means that not available in book, but available in research materials. We consider it for our general discussions in lecture classes, but I have not included that. So I can think that we have some threshold voltage expressions which is almost similar to the MOSFET expressions, but having the effect of 2 gates. Okay. So these are the capacitance we are using here. Normally for MOSFET related calculations, we mostly use 2 capacitance. One is the oxide capacitance, another is the depletion capacitance. But here we have to consider third capacitance, which is coming from the buried oxide layer. Okay, so COXB is the buried oxide capacitance that is also be considered in these calculations. Okay, so these are the basic operations of FD-SOI. Now I will move to the problems of SOI device. There is lots of advantages. That's why SOI device was popular, but our objective is to move to the multi-gate device. So I will just say that what are the problems we are facing for the FD-SOI device? Problems are the field lines. This is an interesting picture. It's showing the field line distributions. Okay, so we have multiple voltages. That means we have the voltage between gate and source, we have the voltage between drain and source. Okay. Now the field lines, of course, it was also available, exist in MOSFETs, But why that is so significant in this SOI device? Because this dielectric constant of this layer. This is the buried oxide layer, and dielectric constant is 3 point, relative dielectric constant is 3.9. That is 3 times smaller than the silicon. So electric field will be 3 times stronger in this material as compared to the conventional MOSFET. So this field line are influencing this channel region significantly, and we are not able to avoid the short channel effects completely for this device. So you can see this type of figure. So the field lines are moving through this buried oxide layer and influencing this channel region for this FD-SOI device. And for the normal MOSFET, this is the whole substrate, this is the whole silicon. So this field line are not so strong in this region, but here this is 3 times stronger as compared to the conventional MOSFET. They are influencing more and more in the channel region. To restrict this field line, there is a ground plane diffusion is created by the researcher. They have created some ground plane, some doped region here, so that it can be restricted by this ground plane. They have also created another gate inside this buried oxide. Okay, this is actually called the silicon on nothing, that is simultaneously invented with SOI device, SOI and SON. This is called the SON, silicon on nothing. They have imagined one gate at this portion, and they are trying to restrict the electric field by using this gate terminal, so this channel cannot be influenced by the additional electric field. But really this device fabrication is not so easy, because suddenly one gate inside this buried oxide will not support the silicon fabrication technology easily. So one can assume it and can simulate easily on TCAD, but this device is really difficult to fabricate. But this is not my intention. My intention to show that ultimately we are moving towards double gate by using this SOI device. Anyway, this SOI gives us VG1, VG2, 2 gates influence. They are going to show some effect of gate voltage, additional gate voltage. So from here, in the culture with SOI device, we are moving towards multiple gate technology. Okay, and that ultimately helps us to eliminate the short channel effect partially. Okay, not fully. So we will move to the next topic. Yeah.
Like the electrical field lines are flow from drain to gate also. So there's an above the. So how the electrical field will flow from drain to directly gate?
Drain to gate. Okay, that if you have field lines will move from any polarity difference. Okay, if you have some polarity here and another polarity there, okay, polarity have some difference, there will be some field line. Okay, but that may influence your operations, that may not influence your operations.
It is through the air.
Here is a dielectric. Okay, here is a dielectric. The lower dielectric, of course, field line can be moving here. If you have unit charge, you know that electric field lines will be spreaded up to infinite distance, ideally. Okay, so if they are very close, of course, field line can influence. Okay, through air also. Here is a good dielectric.
It is depends on like what's the distance between gate and drain, and what is the medium also.
Yeah, of course, medium is influenced. That's why I am saying this buried oxide is a low dielectric constant than the silicon. So field line will be stronger within this region. Okay. So in air also that is stronger, because that dielectric constant is minimum, ideal. In vacuum, what we consider, that is only 8.85 into 10 to the minus 14 farad per centimeter. So that is much smaller. It's almost close to the absolute permittivity. Okay. So now the multi-gate MOSFETs and FinFET. So here this is the train. Again, I have shown here that is published by Gordon Moore. So what was the prediction? That quadruple every 3 years. Okay, number of transistors per chip would be quadruple every 3 years, but really that is not followed because of the short channel effects, what we have discussed till now. So we are trying to find some alternate solutions, and every year when the ITRS meeting happens, they are trying to fix some roadmap that which directions people can move, researcher can move. So in that way, the concept of multi-gate device comes, and probably that will help to continue the prediction of Moore's law. So the here the few things has been written about this same concept, and what I have mentioned, they have considered the 20 nanometer is the gate length. Below that, the short channel effects are too prominent that normal operations become very, very much disturbed. Okay, so if one can consider that what is the typical dimension for the short channel effects should be very much prominent. So as per ITRS, 20 nanometer can be considered. Okay, again, this is no hard boundary, but 20 nanometer can be considered as that limit. Okay, that is written on some documented form. Okay. So now, the brief history of multiple gate MOSFETs. To increase current drive and better control over the short channel effect, SOI MOS transistors evolved from classical planar single gate device into three-dimensional device with a multi-gate structure, double, triple, quadruple gate device. Double gate refers to single gate electrode present on two opposite sides of the device. Triple gate used for a single gate electrode that is folded over three sides. MIG FET, multiple independent gate FET, where two separate gate electrodes can be biased with different potentials. Better we can move to the structure, but before that, you can see one is the family tree of SOI and multi-gate device, just for your idea that from where which type of gate was started to invent, that when they have the researchers start to work with their devices. So if we can consider partially depleted SOI MOSFET, fully depleted SOI MOSFET, it was started around 1980, as we have already discussed. Okay, now that fully double gate MOSFETs, SON, MIG FET, FinFET, Delta FET, they are almost started from 1990 around. Okay, Pi gate, Sigma gate, these gates was invented around 2000. Okay, so now after invention of the concept of double gate and delta gate in 1990, now the FinFET is almost in matured conditions. So you think that almost 3 decades is required to become a device matured. Now, to get some idea about multi-gate device, so you can see the starting is the single gate device. Now the single gate is not the MOSFET. Single gate is our SOI device. Okay, so all the multi-gate concept is based on the SOI substrate, SOI wafer. That's why the SOI linkage is very much important. So you can see that single gate device, we are thinking in that way. We have the buried oxide layer, we have the silicon body, have the silicon dioxide thickness, thin layer of the top gate, and this is the gate terminal. Okay, this is our single gate device. Now, for the SON device, I have shown it earlier that have less physical significance. This is the MIG FET. So you can think this is your buried oxide layer. This is one gate. This is another gate, and this is your silicon dioxide. This is your silicon dioxide, and this is the channel material, channel layer. Okay, so these two gates are simultaneously control the operations within this channel region. FinFET is again the lateral gate, but if you can see, this is the oxide region, this is the SiO2 region, and this is your gate. So their connected gate is looking here. So it can be considered as triple gate device, it can be considered as double gate device. We will discuss on it. This is the tri-gate. Tri-gate means you can consider these two lateral gates and this is one top gate. So this is a tri-gate device. All the gates are controlling the operations, controlling the channels here. So the channel can be formed in this surface, this surface, this surface. Okay, channel can be stopped by the simultaneous effect of all these three gates. So of course, there is more and more control over the channel, but we have seen in the single gate device as compared to that. This is the pi gate device, this is the sigma gate device. Pi gate, just the structure is looking like a pi, that's why it is a pi gate device, but ultimately it's a tri-gate device also, that is the triple gate family we have considered it. Sigma gate, this structure is looking like sigma, Greek letter sigma, so but still this is a triple gate device, so we have considered it within the triple gate family. We have the quadruple gate that is falling in the surrounding gate family. So we have the quadruple gate, so gates in all around, everywhere we have the gate. You can consider the cylindrical gate also, but this is the multi-bridge stack nanowire FETs. So you can believe these are the different words, nanowires, and all these are gate materials. So of course, to increase the gate control over the channel region, people have increased number of gates day by day. Okay, but really, you can simulate this thing in TCAD, but really these are difficult to fabricate in practical way. Okay, yes.
So, what is the advantage of multi-gate?
Of course, simple, that gate control. You have single gate. Single gate is not able to control the channel. Okay, control means I have discussed the short channel effect.
But suppose, sir, we are using the multi-gate FPT. So the antenna effect will be there.
Antenna effect?
Antenna effect will be there. Means the excessive current will be at the gate terminal. Then how to reduce it?
Not clear. Please elaborate it.
Sorry, sir.
Please elaborate it. Not clear.
Suppose we are using the multi-gate FPT. Okay. Then the excessive current will be at the gate terminal. Okay. Then that's why we can say there will be a antenna effect. So how to eliminate it? That effect is known as a.
Maybe I agree with you. Okay, I am not saying these are the ultimate solutions or ultimate device that can be solve this problem. This is one way to increase the gate control over the channel. Okay, maybe what you are saying that gate current will be used or something. I don't know exactly from which point of view you are saying. Okay, but you just think the whole matter in one direction. The direction is very simple. Direction is we need the channel will exist or current will flow between drain and source when we will want. We want that our VGS is greater than threshold voltage, current will flow only that point. Okay? When the
It is an example of FinFET now.
I'll come to the FinFET later.
Yeah.
Okay, so this is the FinFET. Of course, within this all double gate structure, FinFET become practical and most attractive. We will discuss on that. Okay, but this is the possibilities of different multiple gates. Okay, I am saying again, this one can easily fabricate it. Easily simulate it in any device simulators in Silvac or TCAD. You can do it, but you can characterize it. But really, it is very, very difficult to fabricate in existing silicon technology. Okay, so this FinFET, this fabrication is easier and even much easier than the MOSFET also. That's why this technology become so popular, and now the ICs are developed with this material. Okay, so this is not that ultimate solution. Nothing is ultimate. If we can see the short channel effects in FinFET, then that is exist. Okay, but that is better than the MOSFET. Okay, in that way we can proceed. Okay, so here is only and one target to keep that gate control over this channel region, because we have, due to the short channel effect, we have already lost our gate control. Even we are applying any gate voltage, but the channel may, the current between drain to source can be controlled or may not controlled. Okay, so we can see some other structures of multi-gate MOSFETs. So here are some inverted T-channel MOSFETs, and here is sigma gated device. If you see the research paper, you will see a huge number of multi-gate device has been reported. People have worked, they have reported. Okay, they are far from the practical scenario. Okay, they are not matched actually that what is the required. Okay, just briefly I want to say that why that multi-gate MOSFET is actually effective for increase the control over the channel region. That can be explained with multi-gate MOSFET physics. Actually, there is a lot of physical derivations, but I have only added this first slide of that. We have considered here the three-dimensional Persian equations to represent the electric field components inside this channel region. Okay, you just think this is a device having the multiple gates possibilities. Here is your drain, here is your source. Gate can be exist at the top side, gate can be exist at the bottom side, gate can exist at this right side, left side, everywhere gate can exist. Okay. Now this is the point. We are applying the Persian equations here, and Persian equation says this is a three-dimensional Persian equations. We have written this, and in the right hand side we are making equal with QNA by epsilon SI. Okay, so where this is applicable, you know when this area will be completely depleted, then only we can apply this. And we know this whole system is starting from the fully depleted SY device. So this silicon portions must be depleted completely. So easily we can use the Poisson equations within this range. Okay. Now we can represent it in this electric field form. The potentials, the double derivative is represented in form of dE by dx form, dE by dy form, dEz by dz form. And the right side we are considering this is constant because this is fully depleted. If we can consider Q in A is the doping of this silicon body and this is directly constant, all these are constant. So right side we are considering as constant. So these are individually representing the electric field component. Electric field towards X direction, electric field towards Y direction, electric field towards Z direction. Okay, now we can see Z direction is this direction, Y is this direction, X is this direction. Okay, now suppose one direction electric field is increasing. Okay, so at the drain to source is Ex electric field. If this electric field increase, so if this electric field increase, so that will force to decrease the electric field in other two directions. Suppose we are considering simple MOSFET. So one electric field will not exist. In the MOSFET what we have discussed, Ex and Ey are the two only electric fields. So we can remove these Ez electric fields. Okay. You can consider right side is constant. If this electric field increase, so automatically this one will decrease, and that happened actually. That's why we lose the gate control, because drain to source electric field was significantly increased at that point. Now this equation also says or gives us the idea of why we will go for the multi-gate device. If this electric field increase, and if one can add another two gates and increase this electric field, it will suppress this because ultimate right hand side is constant. That gives us the idea of multi-gate device. Increase the number of gate, and if you can increase the electric field in this way or this way, you can suppress this drain to source electric field. Okay, that alternately says with these equations. So this is the primary idea of considering the multi-gate device, so that people can move to increase more and more gates, so that drain to source electric field, which was increased due to the smaller gate length, can be controlled by increasing the number of gates. Okay, that is the primary physics, but we can derive lots of beautiful equations, natural length expressions, so many things that can characterize the multi-gate device beautifully. Okay, so this is our typical FinFET structure. So FinFET, we know that this is the structure we are considering with bulk tri-gate FinFET and SOI tri-gate FinFET. So tri-gate means we have the triple gate. So you can consider gate at the top, gate at the right side, gate at the left side. But this FinFET is considered as bulk FinFET because this fin or finger is started from the substrate directly. Okay, so this is the substrate is directly connected here. But here, this is the SOI tri-gate FinFET. Here, the substrate is started from the buried oxide layer. So this have direct similarity with SOI device, but this one have the similarity with the bulk MOSFET device. So here is the fin or finger, and this is your top gate, this is right gate, and this is left gate. So these are the lateral gate, and this is the top gate. That's why this is called the 3-gate or tri-gate FinFET. You can see this double gate device because FinFETs are most popular in double gate configuration. How the double gate is configured? By adding this hard marks portion. This is some different types of dielectric medium, so that this gate effect will not appear here. They try to restrict this gate effect over this region. They think these lateral two gates are enough to control this channel within this region. This top gate effect should not be here because there is lots of chaos comes, because that is called the corner effect. If these two gates are simultaneously works, so this region will be inverted much faster than this region, because this gate and this gate within this corner is applied more, and the inversion will create in this corner first. So before opening the channel due to the inversion, this portion become open first. So this corner effect is not desirable thing. That's a significant problem for the multi-gate device. That's why in the FinFET, they restricted this top gate and only this is the lateral gate. So channel will be created this area, channel will be created this area. Okay, in that way. So here I have not added no detailed thing of the FinFET, only few steps of fabrications because this is not the position for showing the derivations and physics and calculations. So just to just see that FinFET can so easily can be fabricated. Okay, that's why it becomes so much popular in recent years. So this is one typical FEACM image for FinFET, fabricated FinFET, which is 11 nanometer is the channel length. Now for the FinFET, what is your channel length? This is the channel length. Okay, here is one gate, there will be another gate, but this 11 nanometer is the channel length, but the fin height is 58 nanometer. Okay, so why this is called fin? Because this is ultimately a finger. Okay, finger in brief is called fin. This is called the fin height, this is called the fin width. Okay, so these are the steps, the fin formations, gate stack formations, source and drain extensions, implant, spatial formations, epitaxial, raise, source and drain formations. These are the few steps for tri-gate FinFET fabrication. This is too easy actually. If one can start with SiO2 Si substrate, of course they have to take the SY substrate initially because the silicon body should be on the SiO2 substrate. And then the formation of fin is much easier because by using suitable etching process, one can remove these silicon, additional silicon portions from it. Okay, so there is lots of different technique or methods because our commercial photolithography technique can reach up to 200 nanometer of this range resolutions. But if one can reach this finger thickness is 11 nanometer, what you have seen here, 11 nanometer, this is not the purpose of normal photolithography. Okay, so there was some different technique was used, the detailed techniques also reported. Okay, so finger thickness can be reduced in 10 nanometer, 11 nanometer region. Okay, then after creation of this finger, it can be processed through some thermal oxidations to create a high quality oxide layer over this region. Okay, and then the gate material is deposited. Gate material means some metal one can deposit or one can deposit some polysilicon, polycrystalline silicon, and then some planar method is used to remove that additional material because this portion must be extended because here is the fin, so any deposition technique will show the non-uniform surface. Now here this is the removal of additional oxides, additional gate material. So this portion will be removed. So some gate material is removed from this portion, this portion, this portion and this portion. So this, the fin is again coming out from here and some fin is coming out from there. So they are basically source and drain. So you can consider this portion as source and another portion is drain, and only within this gate portion, the inner portion is responsible for creating the channel. Okay, gate control only over this range, okay, within this fin. Rest of the portion, this will be your source and backside will be your drain. Okay, so now some offset spacer is used because now the source and drain will be extended, because if the source and drain is too narrow, like 11 nanometer, 10 nanometer, so it will show a very high series resistance that is not expected. That's why this source and drain region is extended by the epitaxial growth and it can show some broad view. Okay, so this is the typical FinFET fabrication technique. If you see the fabrication steps are much easier because less number of steps is used to fabricate this. That's why now this device is too much acceptable, but still the modeling part of this FinFET is still under consideration. Lots of different models are proposed. Lots of models is proposed by the University of Berkeley. You can see different research, but now I can say still this FinFET have some openings to research if you want to really do some potential work in simulations mode. So the FinFET and advanced devices can be considered for that. Okay, so also there is lots of extended discussions that FinFET is really overcoming the short channel effects or not. partially it can overcome, but not fully. Okay, so that can also be discussed later. But last half an hour, I'll move to some new topic, different topic, that is advanced material-based field effect device. Really, this area is my area. I am working in this area. So I'll just show you something here. So I can come here, the background of advanced material-based. So see, in my whole discussions, what I have shown, basically, we are moving towards finding out some better device to eliminate the short channel effects. That is one way. Everything what we have discussed in the silicon technology only. Okay, but silicon technology is not the only options. We can move towards some other advanced material, because that now the recent time is the time of new and new materials. Lots of new materials are invented. That is mostly the nanomaterials. Nanomaterials can be considered in 0-dimensionals, 1-dimensional, 2-dimensional materials. So here is lots of opportunity to work with field effect transistors or field effect device, where the new advanced materials can be considered as the channel materials. Okay, we are focusing on the 2D materials in our research mainly, but in between these 2D materials, there is another important material which was considered for fabricating field effect device, that is called the CNT. Carbon nanotube FET become very much popularity for developing the field effect device. We also developed backgated CNT FET in our lab. It works, okay, really, but it's not that not a new materials, because CNT have a large background. Okay, already it has been discussed in multiple research articles, and their properties and their limitations, advantages, all are discussed. We are now moving towards some advanced materials where our main focus is to, we have started working with 2D field effect transistors by using the material graphene. Okay, but graphene was invented in 2004 and matured in 2010 and 11, and last 10 years, lots of people have worked with graphene and graphene oxide. Almost the area is blocked. Okay, there is almost no chance to work, because lots of work already done on the graphene. So now people are moving towards some new materials, advanced 2D materials, which is some way better than graphene, but graphene is the first material which gives us the idea that really 2D can work. Actually, before invention of the graphene, two other carbon allotropes was invented. That is fullerene, that is called the 0-dimensional carbon allotropes, and CNT, which is the 1-dimensional carbon allotropes. But theoretically, people thought that, okay, there will be some 2D materials in carbon form. But when the graphene was invented, that missing carbon allotropes was invented. Okay, but it showed lots of beautiful properties, and that's why people moving towards to find more and more 2D materials. And that is, they found that alternate 2D materials in chalcogenides form. That is called the transition metal chalcogenides. What are the chalcogen? Chalcogens are the sulfur, selenium, and tellurium. Okay, these are the groups. It's starting from oxygen, nitrogen, and then only the sulfur-based, selenium-based, and tellurium-based materials are called the chalcogen materials. And if they create some compounds with transition metals, then they are called the transition metal chalcogenides or dichalcogenides. So the most popular example is the MOS2, molybdenum sulfide. Okay, MOS2, WS2, MOSE2, WSE2, SNSE2, lots of chalcogenides. All these are 2D materials. Okay, they can use for the developing of field effect device. Not only for the mainstream electronics, people can use it for multiple other applications. Other than these chalcogenides, black phosphorus is one of the most popular 2D materials, but this material is quite unstable. If you keep this black phosphorus in open atmosphere, it would be oxidized, and after some time it would be damaged. But property is very good. We prepared this black phosphorus, but after few days, after few seconds, it shows some different color, and then after some time, few days, that work is completely stopped. Okay, so black phosphorus is unstable material, but really that's a very good 2D material. Mexins is basically metal carbides. Okay, that is one of the very advanced materials. We also fabricated mexins in our lab. That is a good material but again, the issue is there. Actually, when you are moving towards more and more nanomaterials, that there will be some that stability issues. Okay, because in normal atmosphere, they will be degraded. but it can show beautiful properties. So that is the challenge to convert this advanced material to a good device related material. Okay, so materials are available in raw form, but they have to convert it for the good field effect device form. Okay, so here how we can proceed for this type of research? There is two ways. When we work with advanced materials based field effect transistors, so the simulation techniques is not so similar what we are doing now for the silicon technology. If you have TCAD and Silvaco, you can work with any silicon technology, okay, but when you are doing with these new 2D materials or any other advanced materials, so what you can do, there is two procedure. One is you can choose a density function theory based tools, okay, DFT simulation tools. There you can atomically design your material, okay, any 2D material. Suppose you want to design it, there is some standard library that will be started from the graphene. You can modify, you can change, and you can implement your own material. Then you can simulate their properties, okay. When the properties will be done, then you can choose any GF, that is non-equilibrium green functions. That's one powerful conceptual simulation tools. So you can use these NEGF functions to study their transport properties. Okay, new materials you have constructed, you have tested their properties. Now then new materials you are configured in a FET form. That means your only drain, source and gate you have, and you are using these non-equilibrium green functions to simulate that. Okay, so recently we are purchasing one software in our lab, NanoDecal. So really I have no idea about simulation part. I have not done any simulation work earlier. So I'm collaborating with other faculties. So they know the simulations part well. So they will do, but ultimately it will help us to develop some simulation based work. So new materials in a field effect transistors, we can proceed with that way. Now the second part, of course, we have to fabricate it really. Otherwise, without fabrications, that simulations is not enough really to achieve a good work. So we are following the chemical vapor depositions as the technique. High-end CVD we have facility now we have. So we can fabricate few layers or single layers of chalcogenides in our lab. So we can use it for the different 2D material field effect transistors fabrication. So I will show the fabrication steps, and then the few fabrication, the source and drain can be fabricated by using suitable photolithography technique, because the photolithography facilities will also be available with us. So I believe up to the feature minimum resolutions of 1 micron we can reach. That means gate length of 1 micron we can reach with our existing facilities. So this whole structure can show you that how we can simulate, and then we can study the properties and transport behavior of the device, and at the same time we can develop the material, we can fabricate the device, and we can test them, and then we can compare both their performance, and we can say that one can be complement of another, okay, because that simulations not be able to show everything, but this fabrication have the limitations, will not be able to reach on 10 nanometer, 5 nanometer gate length. We can reach up to 1 micron. So one will be complement of another. Okay. So in that way, we would like to proceed on the theoretical and experimental approach towards the new advanced materials based field effect transistor. So I'm not going to discuss this basic graphene FET. I'll show you one work what in 2019 I did. So this is the basic of graphene FET. I'll show you the device because it's a first 2D FET. Before that, I have no confidence that we'll be able to fabricate field effect transistors in our lab, and we are able to measure it. But now we have lots of facilities, we are able to do it. But in 2018 and 19, it was really challenging. But first time we observed the field effect transistors with graphene oxide material, and it was used for the chemical sensing applications, and this article was published in IEEE Transaction on Electron Device. So if you can see, we are using the material is called the graphene oxide, not the pure graphene. Okay, graphene and graphene oxide have the difference. Graphene is the pure material, it can show the almost metallic behavior. but that have the huge hydrophobic behavior. Okay, so if we can try to graphene soluble with water, that will not be possible because of the hydrophobicity. But the graphene oxide is nothing but graphene, but there is lots of sp3 hybridizations. Graphene is with only sp2 hybridizations. If we can consider the graphene oxide that has the sp3 hybridizations, that means lots of oxygen functionalized groups will be exist. O minus, OH minus, COO, lots of oxygen functionalized groups will exist. So that makes this graphene oxide soluble with water. Okay, so when we can prepare this soluble graphene oxide solution, then we can easily drop cast it over the silicon dioxide substrate. Okay, that was the challenge actually, because we have not fabricated synthesized this graphene oxide. We have purchased this graphene oxide from Sigma Aldrich. Okay, that's a very well reputed company. So then further we reduce this graphene oxide by removing some oxygen functionalized group from this surface, that is called the reduced graphene oxide. So graphene can be represented in three forms: graphene oxide and reduced graphene oxide. Ultimately we tested with reduced graphene oxide, removing some oxygen functionalized group. So simply the deposition was possible only due to the solubility of graphene oxide with water. Okay, then we controlled way we drop casted it over the SiSiO2 substrate, and then we removed some oxygen functionalized group. So here you can see the structure what we have fabricated. It's a typically backgate structure device. Okay, without front gate, that device can work as a field effect device. Still you can see here the MOS structure. How? So this is your p-type silicon substrate. This is actually the substrate you have, and this is the silicon dioxide, and this is the silicon dioxide. Actually we purchased this substrate directly from the market. We have known vendors. We asked them to control this oxide thickness. They sometimes control this 90 nanometer, sometimes offer us 300 nanometer. So this oxide thickness we have with 300 and 90 nanometer. Okay. Now we have etched this portion from the back side by the hydrofluoric acid, and then this portion has been opened now. And now in the top side, we have deposited reduced graphene oxide. These are the flakes form. Graphene oxide is not a continuous layer. It's a flakes. I will show you the FESM image. So we deposit it by the drop casting method. It's not a continuous, but there is a connectivity from the source and drain terminal. Then after deposition of this film, we use our shadow mask to deposit this gold drain and source electrode. So this is the drain and this is source. Depending on the bias, one can choose which one will be source and drain. So only 3-terminal device this is, no 4th terminal we have. Okay, because we don't have the top gate, we have this source, drain, source and the gate terminal, and this is the VDS voltage, source is connected to ground, this is the VGS voltage. Now what is the MOS junction here actually? Here the metal is this one. Okay, compare this one is the metal, they are doped silicon. Okay, oxide is oxide here, silicon dioxide, and silicon where the channel was formed, here this is the channel with different material. So graphene is the material used here as a channel. So this is our MOS structure, this is our capacitor. Okay, now this source terminal is connected to this channel region. If we can apply some voltage between this source and gate, so basically this capacitive structure will inject some electrons in this channel region. How? If I can apply this positive voltage here, so this is the positive voltage, so I am applying a positive voltage. So if this is a positive, so it will try to induce some negative charges within this channel region through this source terminal. So this is the behavior of normal capacitor, and that is happening here. So initially this graphene oxide show the p-type behavior, p-type semiconductor. Why this is p-type semiconductor? 2D materials have the very low carrier concentrations. Carrier concentrations are normally considered in per centimeter square form. Normally in silicon what we write, that moderate doping is 10 to the power 16 per centimeter cube. But here we represent this is in the order of 10 to the power 12 per centimeter square per unit area, because charges are available in 2D form, 2D sheet. Okay, they are very limited in number. Now you have the graphene substrate, graphene material initially. Now that is oxidized slightly. That's why the graphene oxide is formed. When the oxygen, different oxygen species are adsorbed to the surface, that captured few free electrons over this graphene area. So when the electrons are captured, so then ultimately we can say the holes are increased. Electrons are captured by this oxygen species, so holes are increased, and when the hole is increased, initially this graphene oxide try to show the p-type conductivity. Normally after fabrication of the graphene, it can show the p-type conductivity. Now what happened we are doing here? We are applying the gate voltage here continuously, so we are injecting some electron within this channel, so the hole concentration will be neutralized, and after some time the hole and electron concentration will exactly equal. When the electron and hole concentration will be exactly equal, the device will show the minimum conductivity and device will be considered as off. Further increase of voltage, VGS voltage, electron concentration will be much and much, and then it will show a continuous increment of the current. I will show the behavior, but with this biasing arrangement I have shown the actual scenario. So here this is the typical FESM image of the graphene oxide film that we deposited. So this is the 10 micron scale. This is the single layer of graphene oxide. So here this is the, depending on the darkness, we can indicate which one is the single layer, which is double layer or triple layer. Okay, in that way. So we can measure the thickness. This is called the atomic force microscopy. This is the scanning electron micrograph. This is the atomic force microscopy. We can see this is the portion. Suppose here the atomic force microscopy tip is moving from here to here, and due to this tip transition, we have the depth we have measured as 1.5 nanometer. So graphene is a one atomic layer thin layer, is showing 1.5 nanometer. This is due to we have the oxygen functionalized group at the top and bottom. Okay, that's why this thickness is slightly more than the one atomic thing. Okay, so this is the Raman spectroscopy. Raman spectroscopy is the most important spectroscopic technique which can characterize that really graphene is formed or not. This DG peak, D is the defect peaks and G is the graphene peak. So this DG peak is actually represent that graphene is formed, and depending on the ratio we can predict this is graphene oxide or reduced graphene oxide. Here is the XPS image, X-ray photoelectron spectroscopy, that can show that which type of bonding are exist. So this major peaks is indicating the CC bonding, carbon-carbon sp2 hybridizations, and this CO, C double bond O, C double OH, all these existence are indicated by these different peaks. So in that way we can characterize the material first. Okay, when we can choose any material, we have to characterize it exactly what is the detail of that. Then this is the behavior of the current voltage behavior. So this is ID versus VGS characteristics. We have measured it with a constant VDS 1.4 millivolt, and our ambient was synthetic air, argon and oxygen. Okay, why this ambient was different? Because actually our application is a gas sensing or chemical sensing application. So ultimately we want to use our device for different that type of applications. So here I am showing that everything for the mainstream electronics perspective, but this experiment was done to perform some chemical sensing applications. So we have considered different ambient and different temperatures. This is 25 degrees, 75 degree, 125 degree centigrade temperature. But interesting thing I just want to show you, VGS voltage is started from 0, okay, and this is your drain current. Now when the gate voltage is increased, the current is decreased because initially it was p-type. The hole was the majority carriers. Now when the gate voltage is increased, in this capacitive structure, electrons are injected continuously. Electrons injected, that means the electron hole are recombined and the effective carrier concentration was decreased. This is the point, is called the Dirac point, where the electron and hole concentration is almost equal, and that is the threshold voltage for this device. When this electron and hole concentration is equal, so here it will show the minimum conductance. Okay, so current is minimum here, so it will show the minimum conductance. If we can increase the VGS voltage further, electron injections will be increase and increase more. So in that way we can increase up to some huge distance. So basically here, this is the starting point. One can start from negative voltage also, so they will inject holes in that way. So in that way on-off ratio can be changed. At the starting point we can consider from the negative, or we can start from 0, but the threshold voltage is basically the Dirac point. That particular gate voltage where the current will be minimum is called the Dirac point voltage. So that is the threshold voltage for this device, and on-off ratio can be measured from the on condition, which is normal conditions and off conditions, that is direct point, on-off ratio can be measured between these two currents. Okay, on current and off current ratio. So this is the device is normally on device. Okay, this is the depletion mode device, but this off, the quality of this off is actually important to choose this device for the mainstream applications. Graphene FETs have the limitations because on-off ratio is not so good, and this off, that is a direct point, sometimes may not show that such a low current value. Okay, so however, this work was extended for different purpose. So ultimately, this device shows some different types of amplifications technique. We actually detected methanol is a volatile organic compounds by using these sensors. So by using this RGO FET, and it shows a beautiful sensitivity amplifications under the applications of particular gate voltage. Gate voltage near this 5 volt is showing the highest sensitivity, and also near the 12 or 13 volt it also showed the highest sensitivity. Okay, so it was considered for some different applications. It was showing some amplified response, but that is not relevant to our discussions. So these are few numerical values. This is the mechanism exactly of why this type of sensitivity amplification is showing, but again I will not discuss because this is not relevant to that. Okay, so okay, sorry, I have not shown that. Probably I have removed that conclusion part. Okay, no problem. I can conclude verbally. Okay, so that whole thing is indicate a flow, the evolution of the field effect devices. So I think now it's clear that why I am saying this is a field effect device, not exactly MOSFET. MOSFET should be too narrow actually. It's a wide different types of device, but still that MOA structure will never be changed. Okay, that is the main, the heart of this device. So if you have any new material based device or any device you can choose, but that field effect structure will be same. So this is the tradition, and my intention of this presentation that to explore that different possibility of work. Okay, exactly what we are studying in our book, then slowly that new inventions which was invented in 1980, 1990, that advanced devices are now in mature stage, and what are the possibilities we can do in the recent days. If we want to stuck in our silicon technology, then also fine, we can do some multi-gate related research. Okay, but if we want to move towards some new material based research, then we have to follow that the new technique what we are discussing. If we want to choose some new materials rather than silicon, then we have to change our simulation techniques. Okay, we have to choose new and new methods. Of course, the density function theory you have to choose for exploring new materials in simulation mode. Otherwise, one can move towards the fabrications route. Okay, they can fabricate the materials and device, they can test, but of course that is a very costly thing. And one lab we are developing recently, the complete fab lab in our new workshop building. Okay, so that is under the parts DST project. So this is the project actually have. Under this project we are developing a complete fab facility. We are quite optimistic that we will be able to fabricate that high-end device, and that would be comparable to the device is reported in other labs. So this is completely for the research purpose. So of course, if you are interested, you are welcome, but I think it will take 1 or 2 months time to be completely delivered conditions. So other than we have another project, we have that DFT NEGF Explorer. Okay, we will try to increase the number of users so one can use it. Okay, other than we have our small existing lab, because I have these multiple projects I have completed till from ACRB, MHRD, DST, and some internal grants, DBT, Department of Science, Biotechnology. So this is our small lab. The picture was taken in 2019-20, but now that lots of other facilities has been added. So but I think our bigger lab will be delivered shortly. Okay, so if you are interested, you are welcome. Okay, you can come to our lab, and if you want, you can extend some research. Thank you so much.
One question is from my side, sir.
Yeah.
So you are saying that there is a characteristics between ID and VGS. Yes, yes, sir.
Okay.
So it means it is a characteristics between IDS and VGS, and you are saying that at the dip, number of holes and number of electrons are same. So, but drain current is flowing. So it is due to holes or it is due to electrons?
Yeah, that's a good question. So they're almost equal. Okay.
Yes, sir.
It is very difficult to make it exact same. Okay. If you can increase the resolutions more and more, you will see another point, another point. Okay. So ultimately, it will not be exactly zero, exactly equal. Okay. There's a transitions. Okay. So if you can see that, suppose 10 volt. 10 volt, now we are looking from this graph and we are saying direct point at the 10 volt. Actual direct point, if you see, that is 10.52 volt. If you check it properly, then 10.52, 556, it's a lots of thing. Okay. So exactly zero is not possible. Okay. Exactly zero will be for a fraction of time. Otherwise, there will be some unbalance. Okay. So, actually, if you see that situation is looking like this, a good question. So, if we have the VDS and VGS, this is the typical energy band diagram of graphene. Okay. So, this portion is indicate that electrons and this is the holes. Okay, this is electrons, this is holes. This is the direct point when this is 50% is completely holes and this is electrons. Now this is the situations when the holes and electrons both are exist within this channel. How the current is flowing, I can show you that your current is flowing due to the hole current as well as the electron current. Okay, so there is a current due to hole flow and the electron flow, but the current will be in the same direction. But the holes and electrons, they are recombined with each other, so their effective numbers is reduced. That's why the effective current is reduced. But it's not that there is no electron and hole exist for the movement. Okay, electron and hole exist for the movement. You can see the holes are existing, electrons are existing here. They're exactly zero at this point. Okay, but what about the rest of the channel? Rest of the channel, here is the electron majority, here is the hole majority. So electron and holes are existing, but they're minimum at this point. Okay, and another answer of this, electron and hole have not the same mobility. Mobility are different. If their mobility is dissimilar, if you can think that this is exactly at the middle, but still hole current will be lesser than the electron current. That is another solution. Multiple answers we have. Okay, any question? Oh, sorry.
Thank you very much, sir, for this valuable presentation. Now, I would like to request Dr. Nimish Kumar, HOD, Computer Science Department, to honor our distinguished speaker with the token of love. Thank you, sir. Thank you, everyone. Okay, now we'll take a short break for high tea. Thereafter, we'll continue with